Hello everyone, my name is Mohsen from Loughborough University. The title of my presentation is Adjustment in the Flight Phase of 1 meter springboard forward pike dives. In forward pike dives, divers start the hurdle by jumping from an active leg to achieve a hurdle height. At the end of the hurdle height, they contact the diving board using both feet to depress the board, and then they will be projected into the air to achieve a dive height. They come out of pike, and finally they enter into the water. When divers repeat the same dive a number of times, they typically make very precise and reproducible movement. However, variation is always present in their movement. Movement variability has been traditionally considered as unwanted error or noise that needs to be minimized. On the other hand, recent studies have evaluated its role and shown that execution variability and performance outcome variability should not be viewed as noise only. In other words, variability might have a functional role in human movement. The variability in the diver's joint angle might be viewed as unwanted error that needs to be minimized to improve accuracy. On the other hand, a diver's adjustment of body configuration might be a deliberate compensation for variation in takeoff, leading to increased joint angle variability and decreased outcome variability. There are so many studies that they have investigated variability due to execution or planning. However, there are a few studies that they looked at variability due to correction. We tried to distinguish between execution variability and adjustment. So we aimed to investigate whether configuration changes during the flight phase control the entry angle of 1 meter forward pike dives. In order to answer the research question, we have done a video analysis to calculate the kinematic variables to determine movement variability. Then we used a computer simulation model to determine the effect of variability in dive takeoff conditions on entry angle. A male international diver performed 15 forward pike dives. We used a high-speed video camera to record those performances. A two-dimensional DLT technique was used to calibrate the camera, and we measured orientation and joint configuration angles from manually digitized video. The orientation angle has been calculated as the angle between body axis and vertical. We used an 11-segment computer simulation model of aerial movement to investigate the effects of takeoff variables, takeoff conditions, and body configuration during flight phase on the variability in entry orientation angle. The segmental inertia values were used to calculate the angular momentum, and we used the initial vertical velocity, angular momentum, and joint angle time histories in flight as input into the model, and the model produced the orientation angle time history. The average root mean square in orientation angle time history between simulation and performance was 3.1 degrees. This demonstrates that simulation was closely matched with performance. In the simulation part, we have done two different analyses. In the first case, we have investigated the variability in entry angle arising from takeoff variables, which are vertical velocity and angular momentum. And in the second case, we have investigated the variability in entry angle arising from body configuration during flight phase. In the case 1, we have used the initial vertical velocity and angular momentum of all 15 dives while retaining the joint angle time histories for one particular dive. Generally speaking, we varied initial conditions and we kept the angles the same. In case 2, we have used the joint angle time histories of all 15 dives and while retaining initial vertical velocity and angular momentum for one particular dive. So we varied angles and we kept the initial condition the same in case 2. For example, in case 1, simulation 1, we have used the initial conditions of all 15 dives as input into the model while retaining the angles of dive 1, and we run the simulation for 15 times. The model produced 15 entry orientation angles. This shows how entry orientation angle changes by changing initial conditions only. Case 1 has been done for 15 simulations. In case 2, simulation 1, we have used the angles of all 15 dives as input into the model while retaining the initial conditions of dive 1, and we run the simulation for 15 times. The model produced 15 entry orientation angles. This shows that how entry orientation angle changes by changing body configuration only without changing initial conditions. Case 2 has been done for 15 simulations. The variability in entry angle in the actual performance obtained 2 degrees. Variability in simulation case 1, which is variability in entry angle arising from takeoff variables, takeoff conditions, obtained 9 degrees. The variability in entry angle in simulation case 2, which is variability in entry angle arising from body configuration during flight phase, was 8 degrees. This shows that performance variability was much smaller than simulation variability. This means the diver has done something to minimize the variability in entry orientation angle. This slide is the most significant part of my presentation because this is an evidence to support the idea that feedback control was used. This curve shows the hip angle variability within joint angle time history. As you can see, there is small variability in the early part of flight phase. This means the early part of flight phase is pre-planned or feed forward. There is a large variation in the second half of flight phase. In this period, diver comes out of pike. This curve shows the orientation angle variability. The peak variation in orientation angle appeared in the middle of flight phase. And there is small variability at the start and the end of the flight phase. As I have already mentioned in my previous slide, we found that performance variability was much smaller than the simulation variability because the diver has made adjustment in the second half of flight phase. In other words, diver varied his hip angle to compensate for variation in takeoff, to correct body configuration, and to minimize the variability in entry orientation angle, which is performance outcome. Conclusion. The outcome variability in performances was much smaller than variability in simulation outcome. This demonstrates that feedback control was used. We therefore concluded that the diver adjusted his hip angle in flight to minimize the variability of the entry angle. Adjustment found in this study suggests that variability can have a functional role in human movement. What we found in this study suggests that it is beneficial for coaches to be aware of such adjustments. Thank you.
Thank you very much also for the presentation. It's now open for questions.